In this class, we study rigid body dynamics. Previously, we studied how to describe the total kinetic energy of a system of particles. In general, the total kinetic energy of a system of particles can be separated into two pieces. One piece is the one. This is a rigid body. One contribution is the total mass m is concentrated at the center of mass and with the velocity center of mass. So that is the translational kinetic energy of the system. And then the other contribution is the internal kinetic energy, that is due to the relative motion of each particles with respect to the center of mass. Hence, this is expressed as the time derivative of a relative coordinate, this relative coordinate relative to the center of mass. In general, it is a quite complicated one. It explains everything, just like every lost energy in a macroscopic sense. When we consider collision, there is a completely inelastic collision. It loses all of the translational kinetic energy of two rigid bodies. After collision, the motion disappears, but actually, in reality, when two rigid bodies collide and merge to stop, then the initial kinetic energy of the two objects is shared by every participant. Their vibrational kinetic energy. So even though in a macroscopic sense it stops, but the motion is transferred to the tiny parts, tiny small parts, and it becomes, for example, thermal energy. Anyway, this is very complicated and it is very difficult to describe. However, if the motion of a rigid, if the particles have a fixed relative position, then the motion is unified to make a rotation about an axis. And when we separate them, the motion is expressed, this motion of the internal kinetic energy is described with respect to the center of mass. So this rotation should be expressed as a rotational motion about an axis that is always passing through the center of mass. In that case, the velocity is expressed by making use of the Rodriguez rotational formula for finite rotation, fixed at the Cm. From the Cm, origin is the Cm. Relative to Cm, there is a position of each particle, and this one rotates about the axis that is passing through the center of mass. It has a velocity with omega cross x. And this omega cross x can be further be simplified as omega cross x per, because x is decomposed into x parallel, that is parallel to the rotational axis, that does not contribute to the velocity. Only the lever arm, that is x per, of the particle contribute to the velocity. Therefore, the kinetic energy expressed as proportional to the theta dot square and over a factor is 1/2 mi x per I squared. This one is called the moment of inertia or rotational inertia, because the motion for the internal kinetic energy is expressed in terms of about the origin relative to the origin that is identical to the center of mass. So I put Cm, subscript Cm, to denote that this rotational inertia is measured at the Cm about a fixed axis. Let us consider a simple example consisting of two particles, and they are rotating about the z-axis with the same angular velocity omega. So the position, we can choose the xyz direction in such a way that the xy projection, this is E1 and E2, xy projection of the motion of each particle is the same as this. And there is the polar angle theta, and we use the theta equals omega t. Therefore, this position is, because the distance from the center is d, this one is d, the projection along the z direction is, because this angle is psi, this is d cosine psi, and this is a level arm, the planar radius rho is a d sine psi. Note that this d is not a differential operator, it is just a distance d. Therefore, the position of a particle, this is we call plus and minus. The d plus minus is d, and that is a unit vector with the polar angle psi and azimuthal angle theta equals omega t. As I already explained, the planar radius rho is d sine psi, therefore level arm vector of each particle, they are identical to each other. So d sine theta, d sine psi is the radius, and unit planar radial vector, there is e cosine theta and sine theta, and I have substituted theta equals omega t in here. The velocity depends on this term only because the z component is constant, plus minus constant. So time derivative gives this contribution. We have angular velocity coming from the chain rule, and the unit vector is the planar tangential vector. Using these two, we can compute the angular momentum of the two particles. They are identical to each other, therefore I have doubled the value. Therefore, a single one, x perp cross m x perp dot. Product gives 2 times this double, mass, this mass, and omega in here. Omega is contained in here, and dd, d squared, and sine squared. Because it is along the rho direction and phi direction, cross product should be E3. Therefore, this one is along E3. That's right. This theta dot E3 hat. We recall the Rodriguez formula for the finite rotation, and according to that one, the system is rotating in this way, and this planar radius is always fixed. So angular momentum time derivative is omega cross L. However, omega and L are both parallel in this case, therefore it is vanishing. So angular momentum is conserved in this system. We modify the system in a slightly different way. This one is the same, but this particle, we have a transformation, flip the direction from the opposite side. Then what happens? In the previous page, the direction was tangential and the angular momentum, both of them were the same. The total angular momentum was just the double. But in this case, this one is moving in this way. The other one is moving backward. If you look at these two systems in this side, there is a plane. On this plane, they rotate in a bigger circle. Sure, they do not move along the bigger circle, but in an infinitesimal time, a very short time, it is just like they are moving along this tangential direction of a big circle. In that case, the angular momentum of the two-body system is not along the z-axis, but along a different axis that is normal to this plane. Okay? If it is the case, Rodriguez's rotation formula can be applied. We have omega cross L because L is not parallel to omega. Omega is in this direction. Therefore, L dot varies. I mean, the purple direction represents the total angular momentum, and this direction is not fixed but rotates. This is called the precession. And you can follow the calculation already derived in this page, and it is straightforward to find that angular momentum varies. Next, we consider rolling motion of either disk or cylinder. We consider a rotation. Anyway, the motion of a disk can be described if we write down the total kinetic energy. It should be a sum of the linear motion and rotational motion. The linear motion is represented by 1/2 total mass multiplied by the central mass velocity squared. That is a translational kinetic energy. And another contribution is the rotational kinetic energy about the central mass. And the central mass, we have an axis. This is axis and a hat, and it is rotating with the angle of theta dot relative to the fixed axis to the rigid body. In that case, we have a rotational kinetic energy of this form. ICM represents the moment of inertia about the axis of rotation that is passing through the center of mass. In this case, the system has some constraint when it is rolling over a flat surface. In that case, this point is a fixed point. When it rolls, it has some angle theta. The distance of the center of mass traveled is represented by the r theta. Because this angle theta, when this point touches the ground, what happens? When it touches the ground, it is translated like that. It becomes a vertical, and it used to be angle theta, and this is angle theta. And this point rises up somewhere around here. So during this rotation, rolling motion, the center of mass doesn't change the height and is making a translational motion. And this length should be the same as this length because they are always making a right angle. Therefore, the arc length, this arc length should be the same as the translational distance of the center of mass. So r theta is the delta xc x delta xcm, delta r delta theta. So xcm dot should be r theta dot. After knowing this constraint, we can do many things. This is a circle. This point is fixed. This one is moving with velocity, and this one should be understood as r n theta, r theta dot e1 hat. Let's assume this one is e1 hat. And because this one is fixed and this is a radius r, the velocity of center of mass is v, then velocity of the top is 2v. Double the distance because this radius is 2r instead of r. So in the frame you are fixed on the ground, bottom is 0 and the center has the velocity v, and this one is a 2v, this is a 2r theta dot. We can make a Galilean transformation to transform yourself to the frame where you are fixed at the center. In that case, the rotation rate theta dot is invariant. However, to you at the center, the top is going forward and bottom is going backward, and you are at rest. So what you have done is you have subtracted by r theta dot everywhere. This is the Galilean transformation. So this is a minus r theta dot e1 hat. This was 0 and this is a plus r theta dot e1 hat. Anyway, in the frame where you are at the center of mass, your kinetic energy, you measure the kinetic energy of the whole system. What you have done is just this one, this rotational kinetic energy. You have to measure at the center of mass. This is rotational kinetic energy. And to him, what happens is this guy measure the kinetic energy all together, because at the axis of rotation is about this axis, not this. Therefore, if you compute the total kinetic energy of the whole system by rotating the whole thing about the axis of rotation, that is on the rim, in that case, what you have to do is 1/2 I prime theta dot squared. Theta dot is invariant in both the frame of reference, and you measure theta prime, that is actually this total. This is about the center of mass. So this is nothing but a parallel axis is 0. Using this way, the rolling motion has a constraint that the center of mass go forward with the velocity with the constraint radius times angular velocity. Rolling down the slope, we could have made use of some equation of motion, but as long as we have learned how to deal with the energy conservation, it's much better to begin with the work kinetic energy theorem. The work done by the gravitational force from the top to the bottom with the height difference delta H states that the rotational total kinetic energy of the system changes like that. And because it is rolling, we have the motion, translational motion of the center of mass, and we can compute the total kinetic energy of the whole system's concentrated at the center of mass, that is this term, and additional kinetic energy that is due to the rotation about the axis passing through the center of mass, that is this one. Using this contribution, this energy conservation relation, we can take the time derivative and cancel theta dot to arrive at the equation of motion. And this equation of motion represents the angular acceleration. That is, what's that? I theta dot's the dot. What is that? Angular momentum's the dot. What is that? That is a torque. And you have indeed found the torque on the system. We can apply the same method, or in the general case, why don't we compare the time for travel from the top to the bottom for the two different objects with different mass. If two particles of capital M and small m with different mass slides down without rotation, and the two particles are point-like particles, then there is no time difference at all, because in equation of motion, the mass dependence cancels completely. However, if there is a rotation and the rotational object has some structure, it has the dependence of rotational inertia or moment of inertia. Let's see. The equation of motion we have just derived can be copied in here. This is a torque, and torque is the time derivative of the angular momentum, and angular momentum, time derivative of angular momentum is a theta double dot multiplied what? That is the inertia tensor, the moment of inertia. And the moment of inertia, in case we describe the system as the rotation about the bottom point, this is the rotational inertia. And if we divide into two pieces, translational motion and the rotation about the center of mass, this is the translational motion. This is the rotational motion about the center of mass. Anyway, the two objects has the same mass, so capital M and small m cancels out exactly. However, this structure is different. This one has a moment of inertia 1/2 mr squared with a uniform disk, and this one is mr squared. So we have factor of 2 difference. So this 1/2 appears in the denominator in here, and this factor 1 appears as a 1 as a denominator here. So we have a bigger denominator, so we have a smaller acceleration. That means even though it looks hollow and it may come slide down faster, no, that's not the case. The rotational inertia increases as the mass distribution is concentrated outside of the center, level arm, bigger level arm, and there is a mass distribution inside. Then the resultant value shows that there is a factor of 2 difference. That's the reason why the hollow ring arrived the bottom later than the field one. Okay, even though the radius 2, they have an identical radius. Next, we consider pendulum. Pendulum's problem can be solved by considering the torque equation, but again, energy equation is much simpler to derive, and energy is much easier because it is a scalar, and you know how to describe the change in potential energy, and this Coriolis work kinetic energy theorem, and we take the time derivative to find the equation of motion. In the equation of motion, this is the time derivative of angular momentum. Therefore, this left side should be the torque. Again, we find that the mass is concentrated at this point. This is the translational kinetic energy, and it is rotational motion. We have ICM, rotation about the center of mass. That axis is parallel. This one is parallel to the pivot. Therefore, the angle of rotation for this rigid body, theta, this theta should be the same as the theta that is the angular motion for the string attached to this rigid body. We can extend this idea to consider the collision. This is a completely inelastic collision of a bullet. It does not penetrate, it just is enter into the body of this pendulum. In a completely inelastic case, when they are combined to move together, they are merged to have a total mass m plus m. Even though there is a loss of the total kinetic energy of the system in this collision, the total linear momentum of the system must be conserved. That is due to the action and reaction. Therefore, the final stage, right after the collision, we assume that there is no displacement. It happened a very short time. Then capital V is the final velocity right after the collision. This one is obtained. This is the PCM is conserved. So the total linear momentum is conserved. Using this, we begin with this stage as the initial state of the motion of the composite system of a small m and m. We begin with the velocity capital V in here, and we'd like to find the angle where they stop. First, we consider the total kinetic energy of the system, that is 2m plus m capital PCM squared. And capital PCM is just mv, small mv. So m squared, v squared, 2 times m plus m. This is the initial kinetic energy. We can make use of the relation. This kinetic energy is completely transformed into the potential energy of the system to make a complete stop at this point. So we can make use of the energy conservation formula. And this one is identical to this because L theta dot is the velocity of the composite system. So from here, we can determine the angle where this composite pendulum stops. Next, we consider projectile motion, and we know how to compute the projectile trajectory for a given constant force. And initial velocity of the projectile is given by v0, and that is along the arbitrary direction. Before we solve the problem, actually we know the answer. The torque, what we want to do is to compute the torque, and torque is R cross F, and F is constant. In addition, the constant force is along the z direction downward. And the cross product involves only the perpendicular direction component, the level vector. And initial velocity is v0, and this is a perpendicular component, that is a horizontal displacement. Horizontal displacement is because the initial position is 0. Horizontal displacement is this one. We have angle theta is here, v0, and perpendicular direction, this is a horizontal direction, is a v0 sine theta. This velocity is a constant, and the displacement is just multiplied by time. So v0 t sine theta multiplied by force. That's the correct answer. However, it is just for training. Position, velocity can be computed. Position cross product with velocity multiplied by mass m. Then you will find the answer for the angular momentum, and you take the time derivative, and the answer is exactly the same as this. Next, we consider helical motion. This one is useful for our study in the next semester regarding the motion of a charged particle in a magnetic field. And if you look at the motion from this side, from the z-axis, then it is a uniform circular motion. In addition, if you look at the graph on this side, then it is something like this wobbling motion. And if you make a single turn on the transverse direction, then you go forward by a pitch. This D is called the pitch in the screw-like shape. And why don't you follow the calculation to find the answer? Yo-yo consists of a cylinder, and we wind a string and to apply some tension to the system. And there is a little gap so that we can wind the string. And the string is wound on the surface of this inner cylinder. And the inner cylinder has the radius, smaller radius d, and the radius capital R is greater than d. Important thing in here is gravitational force is applied basically, and gravitational force makes this yo-yo center of mass accelerate downward. We need a force to win the game, so we apply some force in here. And even though our force is not really greater than the gravitational force, we do not require a very, very large amount of force. However, we can make it roll up instead of roll down in spite of the gravity. That's the key mechanism. To solve this problem, we have two linear equations. One equation is the torque, and torque is generated by the applied force, that is a tension. The F is the tension of the string applied with the lever arm with the radius d. And that is opposite to the gravitational force. And you have the torque d cross F, and along this direction it is a rotating counterclockwise. And gravitational force does not contribute to any net torque. The reason is that the cross-sectional area shows we can divide into two identical pieces, and at the center of mass of this left half and the center of mass of the right half, the gravitational force applies in the same direction. However, with respect to the center of mass, the axis of rotation, the torque on the right side is clockwise, and torque on the left side is anti-clockwise, and the magnitude is the same. Magnitudes are the same. So the torque due to the gravitational force exactly cancels. So the only torque applied to this system is due to the tension of the string, and that is that. And in here, the string is wound on the surface of the cylinder. We have this kind of relation. The torque should be the time derivative of total angular momentum, and that angular momentum must be ICM dot theta dot, where the angle theta is measured about the symmetry axis. And torque should be the same as angular momentum's time derivative. Because I is constant in this situation, we have angular acceleration. So the torque is finally expressed as the product of the ICM, this rotational inertia, multiplied by the angular acceleration, and hat is given in here. In addition, the net force on the system is this. Gravitational force is down, and the tension, the F, is up. These two forces are applied in here. So if theta increases, it is rolling down, so it is the center of mass will move down, right? So theta double dot has the center of mass acceleration downward along the gravitational direction. And because this string is attached to the surface, the radius is not r, but d. And we have two linear equations to find the acceleration is like that. If you look at the acceleration is proportional to minus g. That is opposite the gravitational acceleration. In addition, we have negative sign on it. That is, the tension is opposite to the gravitational force. We find that this is the weight, and this is a positive definite. So the denominator is greater than 1. Because denominator is greater than 1, the magnitude of the force applied to the yo-yo is smaller than the weight. The weight is mg. So even though we apply the small amount of force to the inner radius, the resultant acceleration is not going down but going up. It's not a miracle. It is a result of physics, consequence of physics. Next, we consider a precession of a gyroscope. Gyroscope is a kind of top, and you have played with top when you're children. And normally, if it is rotating very fast, it stands up still and rotates very fast. And because of some friction, it loses its rotational kinetic energy. And as time goes on, the angle is not right, but it falls down. Not immediately, but it makes an angle. Here I wrote the angle psi. And then, even though it is rotating about its own axis, there is another rotation in the macroscopic viewpoint. This axis of rotation is actually rotating about the z-axis. So it is rotating. This is called precession. Precession can be understood using Newton's second law of rotational version, and that derives from the relation of rotation omega cross L is tau. And actually this is Euler's equation. That is tau is L dot equals omega cross L. This is an approximate relation for the full rotational version of the equation of motion. This one derives from the finite rotation formula for developed by Rodriguez, because this omega and this is L. These two are not parallel to each other. Because of that, omega cross L, direction of the omega cross L is in this direction, so it rotates about this. This is called precession. Let us first write down the center of mass position. We select the origin of the system at the bottom, and we have a massless rod with distance d. And there is an angle, polar angle psi, relative to E3 hat. And we have another angle of the rotational angle, azimuthal angle, with xy plane. This one rotates the circle, so I can choose the angle phi that is azimuthal angle. Therefore, the position of the center of mass of this gyroscope is capital D multiplied by the unit vector along the direction n hat. That can be described in such a manner. The angular momentum of the gyroscope is approximately, because it is spinning very rapidly about its symmetry axis, then we can make an approximation that L is about its own axis. Theta dot is rotating about this n hat. and the rotational inertia about that axis. This axis is 1/2 mr squared. We learned previously. And gravitational force applies to the center of mass effectively, right? In this case, the center of mass is here. If you want to find out the torque about the center of mass, x is passing through the center of mass, the left side and right side torque cancels. So there is no net torque on this system due to the gravitational force. However, we have a disk in here, we have a center of mass, we have a gravitational force mg downward. Because there is a rod, we have a center here. We have non-vanishing lever arm. Therefore, the torque is applied in here. The torque is applied in here, R cross F. So the direction is coming out of the plane. Or, and here, gravitational force is applied in here. Lever arm vector is here. So in this direction, there's a torque. The torque make the direction, the direction along the rod and head is the direction of the angular momentum. Angular momentum changes along this direction. That makes this gyroscope rotate about the z-axis. I already told you this is called the precession. So we can compute the net torque. The net torque is a d cross mg, but among d, this is a psi. So lever arm is d sine psi, the d sine. Force is mg d sine. Direction is along the, this is the direction. And if you look at the system from the top, this is the d perp, and gravitational force is going down, and the torque is along the phi direction. So that's the reason why it is rotating counterclockwise. When the whole magnitude, this is this direction. Okay. Using this fact, even though theta dot is approximately constant, spinning constant, however, it makes the macroscopic rotation about a different axis. That is the axis. This is that axis is parallel to the gravitational force, and that line extends from the origin, the bottom of the gyroscope. We have various exercise problems, which I hope you can solve by yourselves. Still, there are some linear equations. I hope you are already familiar with solving linear equations. This is a self-test. The total kinetic energy of a system of particles can be described as a sum of a translational kinetic energy and internal kinetic energy. And for the case of a rigid body, the velocity is expressed in terms of omega cross xi bar. And using back cap rule, we can simplify this kinetic energy as 1/2 I omega squared. And I is the rotational inertia about an axis passing through the center of mass. The second one, if the Earth is not rotating, the gravitational acceleration is constant everywhere. However, the gravitational, assuming that the Earth is a sphere, the distance from the center to any point on the surface of the Earth will be the same. The magnitude, at least as far as the magnitude is concerned, the gravitational acceleration must be constant, except that the direction is toward the center. However, that is not the case. The reason is that the Earth is rotating about the axis connecting the North Pole and South Pole. The spinning structure of the rotational nature allows us to have a centrifugal force. Centrifugal force is a non-inertial force because our surface of fixed point on the surface of the Earth is not an inertial reference frame, but is a rotating frame. As far as rotation is concerned, we have a fictitious force. Fictitious force disappears only if we consider in the frame called inertial reference frame. The double time derivative of position vector is exactly the acceleration that is proportional to the physical force. However, in a non-inertial reference frame, we have additional contributions. In order not to be confused with the unphysical force, it is convenient to introduce an inertial reference frame from which we describe the equation of motion that exactly follows F equals ma, and then make a transformation from an inertial reference frame to an actual frame we are living in. This is a way how to find the actual gravitational acceleration on the surface of the Earth. First, we can write the unit radial vector we are familiar with it right now. And then we consider the axis of rotation. Axis, we just make the Earth stand up and North Pole, South Pole, and E3 hat is along this direction. And the Earth is rotating. The Earth is big, which I use the capital omega. And this is one revolution. One revolution, that is 2 pi per day. Next, we introduce the planar radial vector. This is spherical polar coordinate, and we introduce the planar radial vector, and that consists of E1 and E2 with cosine and sine projection. Tangential vector should be phi instead of rho. So I have corrected this. And remember, a fixed point, the subscript E means a fixed point on the Earth. If you look at this point outside in a frame of reference that is inertial, the velocity of that point is just omega cross x, because E3, this axis of rotation, it is rotating about this axis of rotation, North Pole and South Pole. We are here, and this one is xe. Xe is fixed to the Earth, and the Earth itself is rotating. So to the person, standing still in a very fast start that is believed to be inertia. Look at this point, it is rotating. It makes a circular path to the center of the earth. This is a code. And this is omega cross x. And this is a plane, xy plane. And this angle, this is phi, azimuthal angle, phi. And direction of motion is along the phi hat direction. The phi hat is e phi hat. That is written in here. Sure, to the person standing still in an inertial reference frame, E3 is here, E1 is here, and E2 is here. They are fixed to S0. In addition, we can find this an object is not fixed but moving relative to the Earth. Then we describe this one as time derivative, partial time derivative. So on the Earth, it is moving with some velocity. On the Earth, we can see this one only. However, in the inertial reference frame, you can see both of them. Relative to the Earth, it is moving with this velocity. That is a kind of Galilean transformation. And another contribution due to the rotation of the Earth. So omega cross. So in a similar manner, we can compute the acceleration, that is, applying this operator twice. Then the single operation of this operator to the position vector fixed to the Earth, we have velocity relative to the Earth and omega cross the position vector on a fixed point on the Earth. And we repeat this operation once more, and time derivative will give xe double dot, acceleration measured on the Earth, and omega dot cross xe plus omega cross xe dot. Because Earth is rotating with constant angular velocity, we remove this part and we consider only this one. So we have contribution xe double dot, and this one disappears, and omega cross this. However, we also need to take the operation of the omega cross. Then we have omega cross e dot. One more time, we have factor of 2 appears because of that. And this one, omega cross can be applied to this one. So omega cross e appears. There are among the 4 contributions, this one disappears because omega dot is 0. This is the acceleration measured in an inertial reference frame. What is the acceleration measured on the Earth? Then we subtract these 2 pieces to find it. The acceleration measured on the Earth is acceleration measured in an inertial reference frame, and minus 2 omega cross velocity measured in the Earth, and minus omega cross omega. We find this inertial reference frame measurement is identical to the gravitational acceleration measured in the case the Earth is not rotating. And the other 2 pieces are called Coriolis acceleration, and this is a centrifugal. Coriolis acceleration gives on the northern hemisphere, something is moving forward, then it does not go straight, instead it is going to the right, because minus omega cross this one gives this direction. In the southern hemisphere, it is turning to the left, northern hemisphere. And this is the centrifugal force that is toward outside the center. The centripetal force is the actual force that makes the circular rotation. The centrifugal force is, even though it's going straight in a frame, we are rotating. This particle, inertial particle, it is deviating from the center. It's going far away. So that is a centrifugal force. So because of the centrifugal force, the gravitational acceleration decreases. However, when a particle is moving and the omega is smaller than this velocity, usually noticeable velocity, it is omega is rotating just 1 day to pi. It is a very small number. So once particle is moving, this contribution is very large. The next part is the special case of gyroscope with angle of psi is a right angle. So you can review this calculation with an easy way. But that's it for this class. Thank you.